Welcome to Design and Manufacturing Project 4. We are Group 11 and this will be submitted to Dr. Hassan Rashidi for Section B. So the first topic will be the minimum viable product. The minimum viable product or MVP is a foundational concept in both product development and manufacturing. The goal is simple: create the simplest version of a product with just enough features to make it functional enough to validate its feasibility and gather early feedback. This approach minimizes wasted effort and minimizes time to market to begin establishing a customer base and prevent imitation from competitors. A great example is Tesla's early Roadster in 2008. This car just wasn't a flashy debut, it served as a testbed to refine Tesla's electric vehicle technologies, such as battery design and manufacturing processes, before scaling up to mass production. Beyond electrical vehicles, MVPs are widely used in consumer electronics, early stage tooling for small batch production, and even testing new assembly lines. However, MVPs come with trade-offs. While they minimize product development costs and enable rapid iteration, they can sometimes oversimplify a product, leading to unrealistic expectations or poor market reception. Despite this, the MVP strategy remains indispensable in manufacturing as it allows teams to identify flaws early in the process, saving both time and money in the long run. The next topic is generative design. Generative design is an AI powered iterative design process which changes parameters including geometry, materials, and manufacturing processes to produce a range of alternatives to design alternatives to meet set constraints. This allows it to produce highly optimized designs to save time and cost while also helping streamline and automate the trial and error required during the prototyping process. Unlike topology optimization, which has existed for a couple decades now, generative design does not need to start with a preliminary design to work with. This means the role of the engineer can shift from hands-on modeling to defining high-level performance requirements and engineering requirements, allowing for more time to be spent on innovation and problem solving. Generative design is useful almost anywhere for complex design or high performance, ranging from the aerospace industry to soft robots and compliance systems. Since it is often coupled with 3D printing and additive manufacturing, generative design can produce very elegant engineering solutions like the single piece 3D printed LEAP 71 rocket engines, which have recently gained a lot of fame. The biggest benefit of generative design is its ability to generate highly optimized designs, which saves manufacturing and material costs and increase performance. It also helps make the prototyping phase much shorter and faster while fostering innovation and widening up design possibilities. It can also be integrated into CAD packages which are already existing and is starting to show up on software like Autodesk Fusion. On the other hand, it does require significant computing power as most AI driven tools do, which can be a limitation in places with limited computational resources. Since these designs are often quite intricate, they must be manufactured by 3D printing, which can limit material properties in some cases. The next topic is lights out factories. Lights out factories represent the pinnacle of manufacturing automation. These facilities operate entirely without human intervention, running 24/7 to maximize efficiency and output. The term lights out comes from the fact that these factories don't even require lighting since no workers are present. A famous example is Fanuc's factory in Japan, which manufactures robots using robots in a completely autonomous process running continuously up to 30 days without any human intervention. The result: consistent production at a scale and speed unmatched by human operated factories. In practical terms, lights out factories are ideal for high volume repetitive manufacturing tasks such as electronics assembly, injection molding, or the production of precision engineered components. Their advantages are clear. They reduce labor costs significantly, eliminate human errors, and can work in hazardous environments without compromising safety. However, these capabilities come at a cost. The initial setup and maintenance of these facilities are incredibly expensive, and their rigid automation makes them less adaptable to design changes. Additionally, there's an increased risk of cyber attacks or system failures which can bring production to a complete halt. Despite these changes, lights out factories remain a cornerstone of modern manufacturing innovation.
Collaborative robots, or cobots, are a specific type of industrial robot designed to exist in a shared space with human workers. This is distinct from heavy-duty, high-strength industrial robots, which require robust safety systems due to their momentum and speed. Traditional industrial robots are capable of managing payloads of a higher mass and often a greater precision than cobots, but must be surrounded by tough metal cages, lockout-tagout safety systems, and light bar sensors. Cobots, on the other hand, are well suited to lower force applications. They are often built from lightweight materials, have round edges, and built-in limits for force and speed. While traditional industrial robots rely on safety systems to immediately terminate operation if there is a human in the system, cobots are built to operate safely with humans in close proximity. However, their payload capacity and precision is lower than larger traditional industrial robots. Applications of cobots include machine tending, quality inspection, palletizing, assembly, welding, finishing, and many other tedious manufacturing tasks. Many models can be taught by technicians how to perform specific motion paths, and most can be controlled using feedback from computer vision. Additionally, cobots are typically cheaper to purchase, operate, and maintain than traditional robots. By strategically integrating cobots into factory workflows, manufacturers can reduce operating costs and allow human workers to level up to less tedious and repetitive work. The benefits of smart process modeling, automation, and artificial intelligence have many manufacturers pursuing Industry 4.0. However, the cost of creating brand new manufacturing lines from scratch is immense. For example, the Tesla Gigafactory in Berlin, widely acclaimed as a shining example of the Industry 4.0 ethos, took 3 years to construct and cost an estimated $5 billion. Since this level of technological renovation is beyond the grasp of most established companies, retrofitting older machinery and smart technology is an increasingly common trend. The primary benefit of smart retrofitting is the ability to integrate, monitor, and automate equipment already owned or lower-tech equipment that can be purchased at a reduced cost. In some cases, legacy equipment is the only way to perform a specific manufacturing process, so retrofitting is the only way to convert a plant to the new Industry 4.0 status quo. However, there are some challenges associated with retrofitting. Primarily, retrofitting a variety of legacy factory equipment can require technical expertise, both on the side of the retrofit smart devices and the legacy equipment itself. Additionally, retrofitting can lead to custom integration solutions per machine that can be difficult to diagnose or maintain in the case of bugs or updates down the line. Whether it's retrofit legacy equipment or newly purchased modern machines, the data streams from smart factories can be used to model and improve manufacturing processes in real time. Digital twins act as virtual representations of a factory floor, enabling manufacturers to make more informed decisions, particularly regarding process planning and optimization. The patterns and constraints of real factory floor operations are used to create stochastic models to predict and optimize future planning. They accomplish this by automatically or manually playing out what-if scenarios without cost to the actual operations. The results of these simulations can be used to direct task prioritization, job scheduling, and new product introductions. The scope of what digital twinning can accomplish is very broad. While this has the benefit of supporting the goals of almost any manufacturing plant, it comes at the risk of ineffective implementation. Plants that implement digital twin solutions will find greater success if they do so with specific goals and questions in mind. Manufacturing leaders who invest resources in unfocused efforts to clone their factory virtually might fail to achieve their highest possible return on investment without focused effort. Value stream mapping is a technique from Lean Management Toolbox for analyzing the material and information flow through complex processes. Series of interdependent processes are often required to produce manufactured goods. For example, manufacturing a smartphone might involve printing circuit boards, purchasing chips, molding the chassis, assembling components, testing functionality, packaging, and many other interrelated tasks. Value stream mapping highlights inefficiencies such as delays in component delivery, rework due to quality issues, or unnecessary processing. The central purpose of value stream mapping is to identify and reduce waste in core business value streams. Processing steps that do not contribute value to the final product should be eliminated. While value stream mapping can drastically improve the efficiency of manufacturing plants, its implementation can include some difficulties. Value stream mapping can be time-consuming, expensive, and only describe a specific snapshot in time. It can fail to capture the nuance in complex or rapidly changing processes. Finally, identifying inefficiencies in a plant is often easier than implementing solutions to actually reduce waste. However, knowledge of where inefficiencies are is the first step to addressing them, making value stream mapping a crucial skill set for manufacturing engineers and operations leaders.
Hey everybody, this is Aryan, and I'm going to talk about human factors. So, when it comes to manufacturing, human factors are vital. They can be roughly defined as an interdisciplinary field focused on understanding the interaction between humans and systems to optimize the performance, safety, and overall welfare of the industry and the people in it. It involves designing human-centered tasks, tools, environments, and systems that maximize the balance between human capabilities and their limitations. Its main applications include physical ergonomics, such as workplace design, tools, and equipment used; cognitive factors, which handles mental processes like perception, attention, memory, and decision making; and on a broader scale, organizational ergonomics, such as workplace communication or team interaction. It also has to do a lot with product manufacturing, which we'll get into in a bit. So why do we think this is important? Well, in an organizational context, we will see vast improvements to health and safety, productivity, work quality, long-term costs, employee morale and satisfaction, and other factors, versus product manufacturing, where human factors plays a critical role in product planning, idea generation, and design and development stages, allowing for more usable, accessible, and safe products for consumers to use. Gaps between what consumers want and what is available in the marketplace become known, especially. So when it comes to limitations, however, initial funding is high because of um, specialized material requirements. Market pressures and fluctuations occur that change what is expected and how this human factors can be implemented, as well as general measurements of return on investment. They're difficult to gauge. Let's go over our next topic, product performance benchmarking. So having employed human factors, how can we potentially test a product's growth and progression into the market? The answer is product performance benchmarking. Benchmarking involves assessing and contrasting a product's essential performance indicators with industry norms, rival products, or internal standards. The aim is to assess the extent to which a product fulfills its functional, quality, and performance criteria. It highlights advantages, disadvantages, and opportunities for enhancement when compared to alternative products or recognized standards. Processes such as cost-benefit analysis and analyzing user experience rely on benchmarking a lot. These are some common applications, as well as quality assurance. So benchmarking is important because of several reasons, three of which are competitive analysis, product improvement, and customer satisfaction. So obviously, benchmarking can help an organization understand how their product stacks up against their competitors, but also by identifying gaps in performance, benchmarking highlights areas for refinement of a product. Finally, when it comes to customer satisfaction, the expectations and preferences of a customer helps companies retain them, improve loyalty, and overall customer welfare. However, there are limitations that exist. The context that benchmarks are taken in matters. Factors like differences in target markets, user needs, or production constraints, they can lead to inappropriate comparisons. Resources like money and time, they need a lot of that for testing, research, and analysis that go into these benchmarks. Finally, confidential competitor data means that a company can't get access to the full scope of all of a product's data. So it limits comparison making a lot. Let's go over our final topic, FMEA. So along the same vein as benchmarking is FMEA, or Failure Mode and Effects Analysis. In general, FMEA is a proactive, structured approach used to anticipate and mitigate potential failures in products, processes, or systems. It identifies failure modes, assesses their effects, and prioritizes corrective actions to enhance reliability, safety, and performance. It was actually initiated in the 1940s by the United States military. The term failure modes refers to the various ways in which a system or component may fail. Failures encompass any errors or defects, particularly those that impact the customer, and they can be categorized as either potential or actual. Effects analysis is a term that involves examining the repercussions of these failures. So some applications include the automotive, aerospace, and healthcare industries because of their compliance standards. So why is this important? Well, we can already gauge the benefits based off the previous description. There can be reductions in product defects and process inefficiencies, enhancements in customer satisfaction and safety, meeting of compliance requirements for industries like the ones mentioned before, and also support for decision making and resource allocation by, for example, prioritizing risks. However, one key output of FMEA is RPN, or Risk Priority Number, which indicates severe failure modes that demand attention. This makes it easy for companies to track their progress for improvement. However, there are some limitations for FMEA. There can be subjectivity in scoring parameters that go into the final RPN number, and this can make it inaccurate and ineffective. It's also very resource intensive, and it may not take into account current market demands since it provides more of a snapshot of the failure modes of a product rather than the mode's development. Also, this is not a standalone solution. There needs to be another testing procedure used in accordance with FMEA, such as statistical process control. Here are some of the sources that we used in this presentation. Quick disclaimer, this was made only for educational purposes. Thank you for watching this presentation.